I guess we have been discussing about evolution and distribution of galaxies, and we talked about the Hubble law last time and the expansion of universe, and I guess I discussed some details about this expansion of the universe and what do we mean by telling like universe is expanding, right? And I guess we talked about Hubble constant, Hubble law as well, and the Hubble constant, and then we discussed these two examples about application of Hubble's law to find the precessional velocity and also find the distance to a certain galaxy, right? Right, so let me start from here. So let's give us somewhere here, right here. Right, so now I guess every one of you, I assume that you remember what Hubble's law means. And so we discussed about Hubble law and how important it is and how you can apply it to find, distance to a certain galaxy. And also another example of if you are given the distance based on the Hubble constant, you can find the recessional velocity of a galaxy as well. That is how far the galaxy is away from us. And now you can see that we have discussed different things. Now, if we consider the present era, astronomers today have tools that they need to explore the universe almost back to the time it began. Right? Now, so remember that what we are doing in this course is just go back in time step by step. Right? So we have discussed initially about our own solar system and then moved to and discussed about stars and properties of the stars, which should be applicable for every star even in different galaxies. But what we have measured about stars are mostly from our own Milky Way, right? So it's like talking about our own Milky Way. And then we started discussing about different galaxies which are beyond Milky Way and different properties of different galaxies like Hubble tuning fork diagram, those kind of things. Now, then we talked about this Hubble law. When you look for these distance galaxies, we can see that they are moving away from us. So the galaxies are redshifted. And at the same time, Hubble found this relationship between the recessional velocity of a galaxy and the distance, right? So which we called as Hubble's law. Now, actually, based on all this information, now astronomers have tools that they need to explore the universe almost back in time it began, right? Now we can actually go back to the time where the universe has began, and this is as a result of the development of different theories and as well as development of technology, which means we have larger telescopes so that we can go back in time towards the beginning of the universe. And from here on, what we are talking is mostly about this era of, things that has happened in earlier universe. And so we have observed galaxies so far away. And we can see galaxies up to now. I think we can, what we are seeing is that how they were looked like around 10 billion years ago. Right now, the advantage in astronomy is that when you observe something that is so far away, you are just going back in history to look at that. Right? If you have a very powerful telescope, such as the Hubble Space Telescope, you can look at these objects that are so far away. And we have, actually now we are seeing these galaxies which are around, 10 billion years ago, right? And so when you observe these objects, what we are doing is we look further back in towards the time. And so what the advantage is that we can see how the galaxies looks like and how the universe looks like when it was very young, right? So that is the advantage. Now, at the same time, there is a problem that we cannot directly detect the changes over time in individual galaxies because they happen too slowly. Now, if you consider, now even for example, if you think about a small experiment that you are doing, let's say experiment that you are doing in a lab, sometimes you experiment things and measure what happened to a certain quantity with the time, right? So you have a stopwatch and then you try to measure it with the time, whether the temperature increase or decrease like that. But you cannot do the same thing for these measurements that you are doing for these galaxies, because while you can see further back in time, these evolutionary processes are very, very slow. It takes a very long time to have these evolutions happen. Even you probably remember now that even for the stars, it takes like billions of years to go from one step to the other step in their evolutionary process, right? Now the same thing for the galaxies. So they have been evolving for last 10 to 12 billion years, but this evolution is very slow, and because of that you cannot directly detect changes of individual galaxies. So what that means is you can just pick a galaxy and then you cannot observe that particular galaxy with the time to see how it changes over the time, right? So that's not going to work because the process is very slow, right? Now, instead of doing that, what we actually do is we observe many galaxies at many different cosmic distances, right? And therefore, what we are doing is we are looking back times, and we call this as look back time. So what we are basically doing is you just go for, let's say 1 light year, 2 light year, like that. If you consider about the galaxies, especially galaxies, then you go for like 100 million light years, 200 million light years, 300 million light years, like that. You look at like different slices, how the galaxies looks, a sample of galaxies looks like when it was like at 100 million light years away from us. And then you look at the galaxies that are 200 million light years away from us, and then 300 million light years away from us, like that. You just look at these slices one by one to see how galaxies looks like, rather than looking at one individual galaxy. You are just looking at galaxies at different ages, right? Different distances, which means you are looking at galaxies basically at different times, right? So that's how you get the idea about the evolutionary process of these galaxies. And this is, very, very fundamental thing, but at the same time, you need to understand how this differ from the other types of, experiments. So that's why astronomy is a bit different than the other different types of experiments that you do in laboratories, right? Now, this is why actually astronomers develop these larger telescopes, so that it will allow them to look at further back in time. Because when the telescope is larger, when you have a good camera with latest technology, that will allow you to look at these objects that are so far away, which means you can get an idea about the history of galaxies, how they have evolved, right? So this is like one of the major fields now in a major research field in astronomy. And here is an example of one of the images. And just to let you know, you will see a very long captions for these images here. That is I mean, just to, since you are referring these as your notes for the exams, I just need to make sure that you get a bit more information about these images and everything to get an idea, right? And this is a long exposure image made during 70 orbits of Earth with the Hubble Space Telescope. And so which means, you know, the Hubble Space Telescope is in an orbit, so it goes around the Earth, and during, so it has made this image during 70 orbits. So when it goes around 70 times, it has captured the same thing again and again. And then we used to do something called stacking images in astronomy. And this is called a cluster of galaxies, which we will talk in a bit, probably within next few slides. Basically, a cluster of galaxy means a collection of galaxies that are, you know, held together by gravity, right? So we call those entities as galaxy clusters. So that will be the next step that we will be talking, right? And this galaxy cluster has a name that is called Abell 2744, and this name came from because this astronomer called Abell is very famous in galactic research. So he was the pioneer who first observed a large number of galaxy clusters, and then he made the catalog of galaxy clusters. So he was the one who actually gave these catalog numbers, and this particular galaxy is called Abell 2744. Appears in the foreground image, right? So there is something special about this particular image. And so what you can see is there is a galaxy cluster here, which contains around, you know, hundreds of galaxies, several hundreds of galaxies in fact. And these galaxies, actually what we are seeing in is, as I have mentioned here, how they look like 3.5 billion years ago, right? And so basically the galaxy cluster is around 3.5 billion years away from us, right? So this is a Hubble Space Telescope. So Hubble Space Telescope has this capability to look at the galaxies that are so far away. And one reason is that it's on the space, so it's out of our atmosphere. So it is a telescope that can get very clear images due to that reason. And these images right here is mostly these, let me take the laser pointer here. These, you know, whitish color objects that you see here, so they are actually galaxies that belongs to this galaxy cluster, right? Most of them are, you can see that these are like extended objects that you have a small halo type of thing for each galaxy. And remember that we talked about these properties of structure of a galaxy. So we call that there is a new disk, bulge, and halo, right? So that halo is clearly visible. You have a nucleus at the center, and then you have a halo. So that's how you identify these galaxies in an image. And all these whitish galaxies, almost all of them actually belongs to this galaxy cluster called Abell 2744. And at the same time, you can see that there are some bluish objects here. This one is blue. So those are actually blue galaxies. Now the interesting thing here is this Abell cluster has a huge, you know, it's a collection of galaxies. So it creates a huge, you know, gravitational field, and you will understand, or you will get to know about this when we are talking about general theory of relativity, that once you have this huge gravity, it can curve the space, right? As a result of that, as I have mentioned here, Abel's 2744 galaxy cluster acts as a gravitational lens to warp the space and brighten and magnify the images of nearly 3000 distant background galaxies. Now, this is one of the beautiful things that the Einstein general theory of relativity can do, is that there is an effect called gravitational lensing. Right? You probably may or may not have heard about that. What it does is, when you have a huge object like a huge galaxies. Now here we have a galaxy cluster, which means a collection of large number of galaxies. It can actually magnify the objects behind that. So that means objects further away. And this is like a lens, right? If you, I mean, this galaxy cluster can act as a lens. If you remember the lenses that you are using in optics, and this is somewhat do the same kind of thing, right? If I tell it in a simple way. So what it does is, this galaxy cluster act as a lens, and which we call this as gravitational lensing, and it magnifies the objects that are so far away, mainly the galaxies that are so far away, right? Now what this has done here is, this Abel 2744 galaxy cluster has magnified nearly 3000 distant background galaxies, and most of them are actually very blue in color. So that is due to the fact that they still have this higher rate of star formation going on, which means you have a lot of new stars. And when you have new stars forming, so that their temperature is higher, so which means the galaxy looks like blue in terms of its color, right? So that is one reason to have this color. And these galaxies are actually around 12 billion years. Most of them are around like 12 billion years away from us, right? And once again, so what is, in summary, you have a galaxy cluster which is around 3.5 billion years away from us. And as a result of this gravitational lensing, this galaxy cluster has magnified the objects that are so far away from us, so that those objects are also visible in the same image, right? All these blue galaxies that you see has come into this particular image as a result of gravitational lensing, and those blue galaxies actually do not belong to the galaxy cluster. So they are appearing here in the image as a result of this gravitational lensing effect. And those galaxies are around 12 billion years away from us, right? And also it makes sense that they are blue galaxies, because for those galaxies, when it says that it's 12 billion years away from us, that is not so long after the Big Bang, right? So the Big Bang means the theory that the established theory that we will be talking, that we think that how the universe has began, right? And so that's around we believe that has happened around 13.6 or 7 billion years ago. And if we are looking at galaxies that are 12 billion years away in terms of these cosmic scales, what that means is that you are basically looking at galaxies that are created just after the Big Bang, right? Even though it's 12 billion years, which means around like 1.5 or 1.6 billion years after the Big Bang. So that means very early stage of the galaxies, right? You will realize it when we talk about Big Bang, because it is not the galaxies that are firstly created in the universe. It was there was an explosion, and then at that time you had only like subatomic particles, and then they combined to become we call this something called annihilation, to become have this hydrogen atom, and then you have the photons, and then universe became opaque. Like that, there is a process that we need to discuss. And what we are doing here is we are going back to that particular point from where we are today, right? So that's what we are. That's how we are going to discuss about this, right? So that is about this particular image, and right. Now this one right here, the equation that you see here is just something that I wanted to add to let you know how actually you measure the velocities of these galaxies, right? Now, when you look at, just give me a minute here. So when you need to measure the distances that are so far away, we need to measure the redshift, right? First, for a galaxy, right? Now this is done by looking at the spectrum, basically. Now the distance to a galaxy is derived from its redshift, that is how much a line in its spectrum was shifted to the red because of the expansion of the universe, right? So we have discussed that all the galaxies are moving away from us, and so astronomers are measuring this, the measurement that we call as the redshift based on the spectrum of the galaxies, right? So that is clear from the example that you see in this bottom. So the formula for the Doppler shift redshift is normally given as Z. C is the redshift, which is equal to delta lambda over lambda, and that is equal to V over C. Right. So if you maybe you have talked about you know about this equation in from the general relativity, so special relativity as well. But this particular equation, it is always helpful to remember it, right? This one right here, because it's a simple equation that will give you an idea about the redshift of the galaxy, right? So that is basically you measure you take one line and then you measure the shift of that compared to the laboratory frame, and that will give you the value of the redshift. Now I have given an example here. If you have a line in the spectrum of a galaxy at a wavelength of 393 nanometers when it is at rest. So that means the normal condition. If you have a line in this spectrum at 393 nanometer when it is at rest. Now let's assume that this line is measured to be longer than this value. That means redshifted by this much amount. So when you take a spectrum of a galaxy, you don't know how far away, but when you take a spectrum of a galaxy that is so far away, you have observed that this from the spectrum, that particular line has shifted by 7.86 nanometers, right? Now you can use this particular image to calculate the redshift. Redshift do not have a unit, so it's just a ratio between the delta lambda over lambda. Delta lambda means how much it has shifted. So that is 7.86, right? So that is the amount of shift. And lambda is the original wavelength or the wavelength at the rest frame. That basically is what is the value which should be if it is not moving away from us. So that is 393. So you get it divided like this, which is this equation right here, delta lambda over lambda, which you will get the value as the redshift, and this value is 0.02. Right now, once you know this value, now for this particular example, that is 0.02, right? V over C equals 0.02. So that means basically this particular galaxy is moving away from us 2% of the speed of light, or 0.02 C. right? So you can plug the value of the velocity of light, and you will see that this is a huge speed, right? So that's how you find a velocity or the recessional velocity of a galaxy, how fast a particular galaxy is moving away from us. You don't directly measure the velocity, right? So what you are measuring actually is you look at the spectrum of a particular galaxy and you observe how the amount that a particular line has shifted, especially the red shifting, right? Amount of red shift, and then you calculate this value C, and then you find the amount of red shift, and then you relate it to the velocity, right? So that's how you find the recessional velocity of a galaxy, right? So here is I mean, there are few images that I have put here just to give you an idea about what are the capabilities now we have in terms of the modern technology, and how far we can look at from these amazing telescope. Now this is an image made with the Hubble Space Telescope image combined with the Spitzer telescope, as far as I remember. So let me check here. Yes, so it's Spitzer telescope. It is an IR telescope, by the way. So they have combined it to look at one of these galaxies. So this is looking at a redshift C equal 8.68. So that's a huge redshift value, right? So you will realize with the time that this redshift is not a linear scale. And when you have a redshift of 8.68, that means you are almost close to the at the very beginning of the universe, right? Now, if you can convert this into the amount of distance that you are looking at, that will be 13.2 billion light years, right? So that's so far away. And so this particular galaxy right here is what we are looking at from this Hubble telescope image, which is 13.2 billion light years away, right? And right now, when you look at galaxies that are so far away like this, around 13 billion light years away, the things that we have discussed up to now may not work in the same way. That is, that when you look at these galaxies that are like around 13 billion light years away, they don't actually fit into this Hubble classification scheme at all, right? Now, since all of you have like answered for the question that I gave, I hope that all of you remember the Hubble classification, right? So you classify the galaxies based on their shape, and then whether it has a bar or not, and then again the amount of whether these spiral arms are tightly wound or not. You classify the different galaxies into different categories. Now this is okay for up to a certain distance, but the problem is when you look at these galaxies which are so far away from us, around let's say 13 billion light years away, the shapes of these galaxies does not fit into this Hubble classification. So they don't look like elliptical or spiral or barred spiral, or they don't look like anything like that. So their shape is completely different. Right? So that's why I have mentioned here this the distance galaxies observed by Hubble Space Telescope look very different from present-day galaxies without identifiable spiral arms, disk, or bulges. So it is true that we define galaxies and their shapes and their features and everything, but when you look for galaxies that are observed by this Hubble telescope that are so far away, they are very different, and they don't have spiral arms, these bulges, or anything like that. Right? Now, what this suggests is that it is clear that the shapes of these galaxies have changed significantly over time. Right? What that means is when you go for these galaxies that are so far away and observe those, since those galaxies do not fit into this Hubble classification, it is very clear that the galaxies have evolved or changed significantly with the time. So let's say you have a spiral galaxy, that now our own galaxy is also a spiral galaxy, right? Milky Way. But if you look at maybe our galaxy, maybe it is not a spiral galaxy like 30 million years ago. Maybe it is not there as well, right? So we don't know, right? So that's the idea. Now we know that the Hubble scheme works well only for the last half of the age of the universe. So that is the information that we have when you go and look at these galaxies at different slices at different times. What we can see right now is Hubble classification scheme works well for only the last half of the age of the universe, right? So it doesn't work the galaxies beyond that. So that means the shapes and the nature of galaxies are completely different when you go back in time. Now, nearly all the galaxies with redshifts that are correspond to 11 billion light years or more, that is galaxies that we are seeing when they were less than 3 billion years old, are extremely blue, right? So that's what you have, remember that you have seen in this picture right here. These galaxies that came into this galaxy cluster image as a result of gravitational lensing. So I have mentioned that these are around 12 billion light years ago. So they are very blue in color. So that tells us that these galaxies, when they are less than 3 billion years old, so these galaxies are extremely blue, right? And you know the reason, that because they have star formation that's going on, right? So the reason is that a lot of young stars and the star formation in them is occurring at a very high rate than in nearby galaxies, right? These early galaxies have very high star formation rates. And observations also show that with distant galaxies are systematically smaller on average than nearby galaxies. So that is another thing that we can see. When you look at these galaxies that are so far away, they are smaller on average than these nearby galaxies, right? And only few galaxies that are present before the universe, about 8 billion years old, have masses greater than 10.11 solar masses. What that mean again is that at early stages you do not have huge galaxies. You have very small galaxies. Are in terms of their sizes, they are kind of smaller galaxies. And 11 billion years ago, there are only few galaxies with masses greater than. These are just information, right? So there are a few more information like that. And so what has actually happened is, over the time, these small galaxies have collided and merged into build up today's large galaxies, right? So which means you had like smaller galaxies at early stage, but with the time, what has happened is that these smaller galaxies are merged together or collided together to build up these large galaxies, right? So that is what has happened. And so our observations are showing that these galaxies have grown in size as the universe aged. So that means when you look at these galaxies that are so far away, they are very small in terms of the size, but when you look at nearby galaxies, they are very large. So that shows us that these galaxies have grown in their size with the time. Right? Now, another thing that we can look at about during this evolutionary process of galaxies is to look at the star formation rate. And this quantity called rho is Fr is defined as mass of newly formed stars per year, or density of star formation rate in a volume. And this is measured in terms of solar mass per million years per cubic megaparsec. And if we can measure this star formation rate as a function of redshift, we can see that how many stars have formed at any time, right? And then look at how this star formation rate changes over the time. So what we should expect is actually now you have a lot of galaxies that are already ceased their star formation. But when you go for early ages, you should see an increase in the star formation rate, right? And this is what we can see. And this graph right here is you have the x-axis, which is the redshift of the universe, which means basically when you increase the redshift, that means you are go back and look at the galaxies that are so far away, right? And this is that quantity called star formation rate that you have measured. And when you measure the star formation rate, you can clearly see that this is the current time. So this is where we are right now. So when you go towards this side, when the redshift increases, we are going back in time, right? Looking at things that are so far away. And you can clearly see that there is an increase in the star formation rates up to here. So that means earlier galaxies may have higher star formation rates. And then there is actually a decrease beyond C equal to, towards this point, there is a small decrease as well. And there are different explanations for this decrease of the star formation as well. But for the time being, let's get the idea that when you go back in the time, basically it's like increase the star formation rates. Right. Now, this is again, I mean, I'm not going to go through like all these images, and this is called Hubble Ultra Deep Field. And this is a very tiny region of the sky in the southern hemisphere, and very close to the constellation Fornax, and again Hubble telescope image. And so one thing that is so special about this image is actually there are about 10,000 objects in this single image, and nearly all of them are galaxies. Now what you see here is almost all of them are like galaxies. And so you can see, you know that inside the galaxy you have tens of 100 billion stars, right? So which means each of these objects will be a galaxy, and inside that galaxy there will be billions of stars. And you can see like elliptical shaped galaxies and spiral galaxies like that. And here's another image of early galaxies. So I'm not going to explain each and every one, just those are for your information. Now we can see that we talk a lot of things about galaxies, and then how the shapes and the sizes of the galaxies looks like when you go back in time. Now what we know is the stars group into galaxies, right? So most of the stars that you see are normally inside galaxies, right? And so they are grouped in one galaxy. The next question is, are the galaxies also grouped in some way? We have already discussed about that. So what we know is galaxies are also grouped in in a certain way. And we will now start to explore the largest structure of the known in the universe. So that is called galaxy clusters, right? Now, I feel that this may be a good point to stop today. And anybody have any questions up to here? So because what we are going to talk here in the next step is about the galaxy mergers and something called cannibalism of galaxies, and then about distribution of galaxies in the space, which is about galaxy clusters, and then cosmological principle, local group of galaxies, those kind of things, right? So I will briefly, so I'm going to stop today at this point. Because I can start directly talking about galaxy clusters on the next day. Right? Anybody have any questions up to this point? So I will be actually uploading this presentation ahead of time, because there are a lot of information that you need to read in this presentation, which I'm not going to discuss. They're just information. So I will upload this probably today or tomorrow. And I actually may need an extra day, because in this week I will let you know in this week or next week, because for these the last few lectures I just want to go a little bit slowly without having longer sessions.